Yeah, hands on everyone. So the last thing that we did, surface tension, which is F is equal to S into L, where S is the surface tension and L is the length of the surface in contact. So once you got the force F is equal to SL, then the rest of the thing will start looking like NLM only. Like I said, this is the thing that will keep happening henceforth. You will really not learn everything new. You'll learn one or two new things and then the mechanics will come up again. So let's see a few questions on this. So in the last class, we discussed in detail why is this surface tension is coming and everything. So let's see a question. So we have a V-shaped rod, angle theta. You kept a rod here. Light rod or massless rod. And you attached a block of mass M here. And here we have a soap film. Surface tension S. This length is L. This length is L. And gravity is present. So find M if the system is at rest. So basically, last time, remember I showed you that video there, we had a rectangle like this and the soap film is pulling that rod left and right. So find M for equilibrium. If the block is pulled down by X and released. So when it is in equilibrium, you caught the block and you pulled it down by X. And then you released it. Find the acceleration of the block. Be careful, a soap film will have always two surfaces. So that S into L will become 2 into SL. That is completely wrong. Solve properly. Your answer didn't have any theta, nothing. How did you get an answer without theta? Try.
Sir, the axis from equilibrium position or from the
Yeah. Pull
point,
down by from equilibrium. Which point?
like the V intersection point of both the rods.
No, from equilibrium.
Okay.
Block is already in equilibrium, right?
Yes, sir.
Hmm. That looks right, Samyak. Arya, आंसर चेक करो एक बार. I think you messed up somewhere. Let's see. First thing. So the rod is here. Now remember in the formula S into L, L is the length of the soap film in contact. So it is just geometry here. So from here, drop a perpendicular. This angle will be theta by 2. This angle will be theta by 2. If this length is L, then this length will be L sine theta by 2. And this length will be L sine theta by 2. So now when you draw the FBD of this rod, the soap film is pulling up, which is S into the length in contact, which is 2L sine theta by 2. Is that making sense? The soap film is into 2 because there are two surfaces, and your mg. There, we'll get it one step. So 4SL sine theta by 2 is equal to mg. Got this? Clear, na, Shihari? Got the thing? So that you should take this L, getting it, not this L. That is a catch there. All clear with this thing. Important, huh? You should know, like this is the starting there. Now in the second part of the question, you're saying you're going to pull it down by x. Now when you pull it down by x, you initially used to be here. Now you will go somewhere here. So when you pull this down by x, so this is also x. This would be theta by 2. Now when you pulled it by x, you got an extra length here. This is x tan theta by 2. So whenever you pull it down by x, you get an extra length there, and this is your 2L tan theta by 2, 2L sine theta by 2. So the length of the rod in contact will increase. Now what is the forces? So on the rod, it will be 2 into S into the total length will be 2L sine theta by 2 plus 2x tan theta by 2. That is the total length of the rod in contact with the soap film, and this will be your mg, and this will be your acceleration. You can clearly see this will be 4SL sine theta by 2 plus 4sx tan theta by 2 is equal to mass into acceleration. Minus mg is equal to mass into acceleration. But I know 4SL sine theta by 2 is nothing but mg, so this term and this term are gone. Therefore, we get acceleration is 4s by m tan theta by 2 into x. That's your acceleration. M ka value, you can get it from here and substitute. So you would get. But understood what we did, everyone. It is all about length. Somehow, if you can find the length, then it will be 2 into s length is minus mg is equal to ma. The moment you wrote force is surface tension into length, your surface tension is done. After that, it is all NLM. Is this clear, everyone? All got this? Next one. Next one. Clear, na, Devanshi? Ashvi? Trishi? Clear? Utsa, got this? Next thing. We have a semicircular frame. And inside we have a soap film. Always, the moment I say soap film, remember, 2 aayega. Most people goof up that, so be careful with that. So there is one surface on the front and one surface at the back, which you can't see the back surface. So here, how does the soap film exert force? It acts perpendicular to the line in contact and parallel to the surface. So surface tension force. I think the best way to imagine a soap film, right? Did you ever, stood on a trampoline? So a trampoline ka membrane kaisa hota hai? It is kind of like that. So if you see, the soap film is actually pulling this perpendicular to the surface. Find the force acting on the semicircular wire due to the soap film. It's an important one. Let's see. Standard result. Find force on semicircle due to the soap film. Right, Utsa? In the previous question, it is SHM. A is proportional to X, so that will be omega square. We will see that in oscillations. I didn't teach you SHM, so I didn't talk about any SHM thing right now. So in the previous question, if you just leave it by X and pull it by X and leave it, it'll keep oscillating up and down. Let's get this. You have a semicircular frame and you have a soap film. Now remember, you can't say S into pi r into 2 directly because all the forces are not in the same direction. Force is a vector quantity. You just can't add them. You have to add them vectorially. Let's see how will you integrate this. Take a minute. Pi r. Vanshika, dimensions match नहीं हो रहा है. Force is S into L, isn't it? You can't get r power 1 से ऊपर you can't get. Right, Arya. Let's see. Now, the integration is important. Huh? So from the center, at an angle theta, take a thin piece d theta. I'll show you something even faster actually without doing this. So on this thin piece, this length will be r d theta. So your surface tension force will be along, it's pulling here. This will be the force, which is how much? S into length r d theta into 2 because there are two surfaces. That is the force. If that is theta, this is theta. So the force on that small arc will be 2srd theta, vector form, minus cos theta I cap minus sine theta j cap. This is the force on one arc. So whenever you have to integrate, get this in terms of a vector and then integrate. Now the force on the semicircle will be 2sr. Let's put the minus sign outside. Integral cos theta d theta. Actually, you can see here and guess there will be no horizontal force. All the forces will be in the vertical direction. I cap limits will go from 0 to 180 degrees. Because when you start here, theta is 0, and when you go to the left side, theta is 180. Plus integral sine theta d theta j cap 0 to pi. Now, why I'm teaching you this integration, because tomorrow someone will come and say, this surface tension force S is weird, okay? It is like K into sine theta. Meaning it is not constant. The surface tension force is changing with theta. Then you should know how to do this thing. And then when you do this, you actually get this term will be 0. And this term turns out to be a 2 ka value. So minus 2 actually. You can integrate and check it out. This much you can handle. And this thing comes out to be 4SR. That will be minus cos 2 ही आएगा. That will be minus j cap. There, that's your force. There's a much faster way to do. If you guys remember, projected area, we can use projected length. Now, what projected length says is, again, what is projected length? The line joining the two ends of a curve. Straightforward. So if you give me some random surface area like this, and if you say there is a soap film inside, so all you need to do, take this point A, take this point B, and join a straight line. Again, same logic, huh? Doesn't this become a closed figure? If you have a closed figure, what is the total force acting in all directions? Zero. That means the force acting on the curve must be equal to the force acting on this straight line. So force acting on the curve will be 2 into S into the length from A to B. So this length is called projected length. So without integration, you'll get this. Again, this is valid only when S is constant. So for some reason, if they mess up S ka value, you can't do this. So just like projected area, you can use when constant pressure. You can use this when S is constant. And so using this logic, if you try to do the previous question, you'll get it pretty fast. So if you take a semicircle, the projected length will be 2r. Therefore, force will be 2 into, because there are two surfaces, S into 2r. Done. आगे एक step में answer. Clear with this? So remember this projected length. This will again come later on in electromagnetic induction and magnetic fields. So this projected length and projected area, this concept will come in almost 6 different chapters. But all clear with the integration? Meaning we can prove this mathematically also. See, if you have any random curve like this, so if you take a point here, let's call it dl1 bar, and if you take one more point here, dl2 bar, and if you take one more point here, dl3 bar, and so on. This will give you a force F1, this will give you a force F2, and so on. So F net will be 2 into S into the summation of all these vectors, dl1 bar, dl2 bar, and so on till dln bar. Do you guys remember polygon law of vectors? If you have a lot of vectors, joined them head to tail, then the resultant vector is from the remaining tail to the remaining head. So resultant of all these vectors will be AB bar. This will be 2 into S into AB bar. Make sense? So you can prove like this also using vectors. But you can also argue like if it is a closed figure, then it will be 0. You can figure out from there also. Any doubts on this? So there, integration, projected length. Projected length is good, so be careful with that. So if I show you a few more examples of projected length, again, if you have random amoeba, it doesn't matter. Take the two ends, join them. This is the projected length. If you take a closed figure, the projected length is 0. That means force is 0. There was like a question like this in JEE Mains once. They said there was a frame like this. This was A. This was B. This was C. And they said this entire inside there's a soap film. The question was find the force on the soap film. So it is clear this and this is your projected length. So this length is nothing but A minus 2C. Therefore, the force on the frame is 2 into S into A minus 2C. बस हो गया एक step में. Clear with this? So what people did, they were trying force on this, force on this, force on this. Each section they are trying to find. They got the same answer, but project length will save your time. Clear? Next thing. Before jumping into the question, let me show you something. Look at this. So you took a big ring there and you kept it in a soap solution. Can you see that film? Soap film. So that is a soap film there. There it is shiny and all. This guy took a thread and he placed on top of it. Now, if you see nothing happens, it just remains in any random shape. So if you put it there, it just remains in any random shape. Why? Simple reason. There is a soap film outside, there's a soap film inside. Both are pulling in both the directions, so net force is zero. But what if you pop the soap film inside? If somehow you can pop the soap film inside, then what do you think will happen? The soap film outside will pull it in equally in all directions. So if you pull something in equally in all directions, what shape do you get? Circle. There. Can you see the circle? There, he kept one more. You pop, there, you get a this thing. So the thread actually becomes a circular thread. If you just remove the thread again, it is gone. So clear? So let's say we have a soap film. Someone took a thread and they just placed on it. This is a loop of thread. Now, if you look at this, the soap film is pulling inside and the soap film is pulling outside also at every point. Since F net is zero, it remains in some random shape. Then what you did, you broke that inner soap film. And we observe it becomes a circle of radius r. So this becomes a circle. Again, simple reason because the soap is the surface tension is pulling it outside. And the radius of the circle is r. Find the tension in the string. Just to show you that context there. Hmm, there, this is a picture initially. This is the picture when you pop it inside. Let's get this.
So
Remember where we
what?
saw this kind of question before? Are
So like, what is that small part there, like just beside the circle?
that is also another. अरे that is just when you make a loop, थोड़ा thread बच जाते हैं ना record. Never made a thread का
Oh,
loop क्या?
अच्छा नहीं. I thought कि it's a complete thread.
How will you get a complete round circle thread? Where did you see a last time a round circle thread? बताओ.
Maybe they
You
made
may,
one.
they'll make it one for you and me for an experiment. They just took a thread, they made a loop, तो थोड़ा side में बच गया था बस.
So it's a
Use
knot. I get
rounds.
it now.
हाँ और कुछ नहीं आता. How do we get this thing? We have seen this in circular motion if you remember. Remember where we did this thing? See, now since it is pulling in all directions, we have done this in circular motion. I told you to remember, it will come in 6 chapters. So we take a small slice. Again, I'm exaggerating the figure. This is a very, very small piece, d theta. Anyone remembered? So when you take this small piece here, we have tension. We have tension here. This will be d theta by 2, d theta by 2. This piece will be d theta by 2 and tension. And this will be the surface tension ka force, which is 2 times, because there are two surfaces, S into r d theta. So you can say 2 times sine d theta by 2. If you remember in circular motion, this used to be equal to the centrifugal force. Here it is 2s r d theta. For small angle, sine theta becomes theta. So we get tension is equal to 2sr. There is a faster way to do. You can do much faster. But for that, you need to know the projector length. Take FBD of half string, okay, half circle. If you take FBD of half circle, then we have an half circle here. Then this will be tension, this will be tension, and this will be projected length, which is 2 into S into 2R. You can say 2T is equal to 4SR, T is equal to 2SR. That is faster. If you take a semicircle, the two strings are pulling down, and the semicircle ka force will be 2 into S into 2R. So this alternate way is faster, but you should know projected length. So this thing, where did you see the first time? You saw this thing in circular motion. The question 14, page 59. Remember this thing. Again, this will come in elasticity. Page 60. All clear with this? Yeah, most of you got it. Now, if there is a force, then there is also energy. We define something called surface energy. Again, a small chapter, just like viscosity. So if you take a rod here, if this was your soap film, yes, and this was your length L. Now, to keep this in equilibrium, you have to apply some force, or else the soap film will pull you inside. So F external, and this must be 2SL. So let this F external move the rod. This is a movable rod here. So let F external move the rod slowly, means you're applying little more force every time. move slowly by x. Then your picture becomes like this. So what is the work done with external force? So work done by this F external force will be F into x. So this is the distance x which you moved, which is 2 into SL into x. Now, if you actually write this, work done by external force is change in potential energy plus change in kinetic energy. Kinetic energy is 0 because you're moving slowly. So we get change in potential energy will be S into 12x. So what is this 12x exactly? This 12x is nothing but the change in area. There. So this part shaded area which I'm drawing, this is your change in area. There, this is your formula. The change in surface energy is simply surface tension into change in surface area. Remember, for a soap film, there are two areas, front and back. You should take the total surface area. This is your second formula, everyone. The first one was force is S into L. Second thing, energy is surface tension into change in area. So now you need to think about this exactly. Okay, so what is exactly happening? You know, whatever work you're doing, this is becoming energy, but how? Let's see that in the next page. But have a look at this. So mathematically, this is how you get energy. Let's try to understand the meaning of it. Like this energy is like coming exactly from where it is going. Clear? Now, what is happening? If you remember in the beginning of the story when we started, we said the molecules on the surface have a net downward force or net force which is pulling inside. Now, if you take a liquid in a gravity space, gravity free space, so let me ask you something. Let's say, we take 100 people and place them in a room, and the room is getting very, very cold. If you leave these 100 people, what do you think will these 100 people do? Do you think they'll all will sit separately? They all will try to huddle up, right? Now, if they all are trying to huddle up, where do you want to be in this group? You want to be on the outside or inside? You want to be inside, isn't it? So that it is warm. Now, if all people have equal forces and everyone is trying to push inside, then the shape you get will be a circle. In a 3D, that will be a sphere. So if you see penguins, right, during winter, when the temperature drops to around minus 35 degrees in Antarctica, these penguins actually form a groups. And what these penguins do? So the penguins are like, in a queue. So this penguin goes outside, this penguin comes inside. This penguin goes outside, this penguin comes inside. So the penguins keep on rotating inside and outside. So the penguin will stay outside for some time, then it comes inside. Then it goes outside, then it comes inside. This way, right, they take places one after another so that the entire group survives. If they get greedy and if you just stay inside, the outside penguins will die and the next layer of penguins will die and eventually you will die. Like this, they survive for almost a month or more in that harsh winters in minus 35 degrees. So something similar happens here. So all these molecules on the surface, they have a net downward force. So everyone wants to go inside, but remember there is no place inside. And if everyone is pushing with equal force inside, the only way you can get is a spherical shape. So basically think of like this. Since there's a net downward force on the surface, no one is actually happy being on the surface. They are kind of unstable. They're not in equilibrium. So molecules on the surface are not in equilibrium. So molecules will try to avoid being on the surface. And whoever is on the surface will have more energy because of the downward force. Unbalanced force. So that means if you take a liquid drop and put it in a gravity-free space, it becomes a sphere. So there, you can explain this in terms of forces. And by symmetry, it forms a sphere. So that means if you have more surface area, means you have more molecules which are not stable, which are on the surface. That means you have more energy. It forms a sphere. There. Now we understand why the energy, the work done by external force became S into change in area. So think of like this: more energy you have, more molecules on the surface. More molecules on the surface means you have more surface area. Is that making sense? You're putting more unstable molecules on the surface. That means your energy is increasing. So your surface area, when it increases, your energy also increases. Right? So molecules on the surface possess more energy than molecules inside. So in a liquid, all molecules are not identical, even though they are chemically same. The one on the surface are a little more messed up. You can think of like this, ever went to a concert or a rock show? The people who are standing on the first two, three lines and the people who are little far off, they behave differently. Ever been to a rock show? You should see. The people who are in the first two, three lines, they go just crazy. They're just hitting their head, they're jumping, shouting, howling, and they're doing all shit. People who are in the last corner doesn't give a shit. They're busy sitting there eating their Frankie or pizza or whatever. They're both chilled out. Because it's like anyway, it's not that. So people do behave differently when you're sitting in the front and at the back. So more energy than molecules inside. When we are in second year IIT, we had a rock show. IIT Madras, we call it Shastra and Sarang. Shastra is the tech fest and Sarang is your cultural fest. Mumbai, they call it Mood Indigo, the cultural festival. So it goes for 4 days in Madras. Okay. So all 4 days, morning you have all these workshops and everything. It is fun, all events. Evenings you have something major, like first day 6 to 9, it was some dance show from different teams, and second day 6 to 9, 6 to 10 actually. It was the rock show from French band. From Europe, they brought a rock band. Third day, it was some classical, right? And fourth day, kuch to tha. It was long back. I think I was in second year. I think second day was classical. Third day was this. Classical, we went thinking it will be boring, but that was quite interesting. They brought the India ka best violin player, India ka best sitar player. And when these people are playing, it was really like, even though you're really not that keen into this music, classical and all, but it was mesmerizing. So third day was a rock show. Getting it, we all decided, yeah, we'll go there and we will just make a lot of noise. Right? And it was fun. So what I did, we all went to this thing and I told everyone, boss, once the rock show starts, we will take out our shirts and we'll start swinging. They all are like, Arey, aisa kaisa karenge? We will not do it is sad and this. I said, you start, we will all come back. I said, theek hai. So we went, rock show started. 1 hour ho gaya, they're singing something. We're not really understanding, but theek tha. It was, people are all dancing, vibrant, everything. I took out my shirt and I started swinging. Seeing me, others all started removing the shirt and they started swinging. What they didn't realize, I was wearing two shirts. Getting it? I didn't tell anyone. I just wore two shirts because in a rock show you can't see. So I just took out one shirt and started swinging. They saw that as a signal and everyone started doing. Security came. They saw whoever is not wearing shirt. They took them and throw them out. So I was just hiding there. I already have a shirt, right? I just dropped the shirt in my hand and I'm safe. So the rock show went on till 10:30 was the deadline. We are like one more karke. We went on till 11:30. Then the dean came. The dean came and said, you guys have to stop now. Then everyone requested, sir, half an hour more. He said, okay, 12 o'clock you have to shut it down. 12 ho gaya. Then again we are one more. The dean got pissed off. He went, he took that, power supply hota hai na, he took that, kya bolte usko, the fuse. He removed the two fuses and went to his house. The entire stadium just became dark. Power supply went off. Emergency lights were on, and everyone got kicked out from the stadium. So it was fun. Matlab, that was my first rock show in life. Right? We are literally catching people and throwing them in air. Yeah, we are catching them anyways. So we are doing any nonsense. कुछ भी कर रहा था. And then हो गया. And for next 2 days, I was humming that music. करके. Then one of my senior called up. I was in second year then. I said, "Do you know what you're singing?" I said, "I don't know." "Do you know what language they're singing?" I said, "English." No, I said, "Idiot, it was French." Yeah. So they came with a rock show. They are singing lyrics in French, and we are so idiots, like we didn't even know what they're singing, and we are humming their music for 2 days. Means we didn't even understand a single lyric there, and we are there in the rock show for 5 hours. That so उसका नाम भी कुछ तो था. So they sold shirts also. Yeah, I don't know. We did all crazy stuff. It was fun. So after that, next year they brought one more rock show, but I think by then I was a little chilled out. Like, okay, yeah, we had fun. Once you reach third year and fourth year, by fourth year you're like almost like a retired person. Yeah, you're like busy with your company ka placements, project work and all. You're just chilling out. I think the first year and second year you go crazy. But third year you become more mature. Fourth year you're a retired person, ancient. So anyways, so it goes like that. So molecules on the surface, right? They have more energy and they're wild. So possess more energy than molecules inside. And that's what I'm telling you. Seriously, put some work, go to a good college. When someone asks me, na, sir, IIT क्यों जाना है? You will study knowledge and all. Yeah, that's all bullshit. But main thing, right? You actually get a really good peer group. Main thing is that what IITs may the biggest plus that you get, yeah, they'll teach and all. I'm not denying it. That is okay. Right. But the kind of peer group you get, the kind of friends you get, it is very difficult to get them. If you join any local college, you will not get people like that. Aisa socho na. People who came to that IIT, right, with you in the class, all these people have worked hard. These people are ambitious. You will be sitting with them and studying with them for 4 years. And when you pass out, you really make good, connections with them. And this thing that I have seen in life, no matter how talented you are, if you don't know the right people, you won't grow. Getting it? You might be superb, awesome, but if you don't know the right people, you'll not get the contact. I'll tell you, it happened with one of my batchmates. There are many people, but this is one thing that I always remember. After we passed out, 12 people got selected in Sony company from our batch. Good company. All the 12 people joined there, and they realized this Sony people just hired them for marketing. Getting it? So they are like kind of nonsense. They took them and they're just making them do very trivial work, right? And then these people realized what they did, right? They used to get clients from outside. And you know what used to tell them? Sir, on your project, we have 12 IITs working on your project. And the client used to feel very happy. Oh, IITs are working on my project. And the project could be done by 10 standard kids, it seems. You can teach the 10 standard kids Excel within 1 week, and the 10 standard kids can do. So all the 12 got really pissed off, like, boss, we are not learning anything here. Yeah, they're paying good, but there's no learning. See, money is important, but not first 5 years. First 5 years is learning is important. So all the 12 people quit the job in 3 months. They left the job, literally. And then this guy applied for Amazon. This thing is 2010 ka baat tha. Amazon said, boss, you are from Sony. It is not related to our company, so you will not allow you for the interview. They didn't see his resume also. And then this guy called up one of my friend who is in Amazon. Now they are classmates. And he said, yeah, I'm trying to apply like this. Abhi main kya karu? He said, theek hai, do one thing. In computer science, you have all these data structures, arrays, and all that stuff. There is something there. He said, these are very important if you're working in Amazon. So he told them what to learn and everything. And this guy started learning. And he said, after a month, you learn all this stuff, right? I will take 1 or 2 mock interviews for you. You're getting it. See, no one will do this much for you. But you're my friend. I will do it for you. You're getting it. That is a kind of, the friendship you have. I have seen this happening a lot. Why all that? Last year, some person randomly called me. And the first thing he started is, sir, I'm a 2016 student. I passed out in 2010. I don't even know who is this guy. I'm a 2016 passed out student from IIT Madras. One of the senior gave your number. I'm into teaching. I want to do something, blah, blah, blah. Right? And the first thing I said, college kaisa hai? Getting it, I don't know who is that guy. Nothing. The only thing I know is that he's my junior. I said, "ठीक है, what do you want? Tell me." And I spoke to him almost for 40 minutes. If it is someone else, I won't even give 5 minutes also. I wouldn't even lift the call in the first place. Just because he said from IIT Madras, my college, so I was ready to talk to him for half an hour. This will make a huge difference going to a college. So then this guy, Amazon mein na, he did everything. Then his friend said, "TK, give me your resume. I will forward it to you as an employee." Now see, if an employee forwards a resume to HR, HR will look at it. Right? So the HR said, "Okay, fine. So you bring that, you bring that guy." And this guy went to the interview. He did really well. Now see, this guy is talented. He learned everything in a month. But Amazon people are not ready to call him to the interview because he worked in Sony. Just because his friend is there in Amazon and that guy recommended, "Boss, take it on me, trust me, he's really good." And they called him for an interview. He did well, he got selected in Amazon. He worked in Amazon for 3 years. Then he applied in Google. Now he applied in Google saying, "I worked in Amazon, not Sony." Google said, "Okay, from Amazon, great, come." He went to the interview, he cracked it. He worked in Google Hyderabad for 2 years. Then he got promoted, he went to Richmond, somewhere in US, the Google main head campus. Now, the reason he went is because he knows someone in Amazon. I have seen contacts working like this. I have one of my friend who was in civil engineering, right? And that guy got bored with civil and he wanted to do an MBA. But to do an MBA, he didn't have the business exposure. So one of my junior had his own company in Hyderabad. So when I talked to him, "अरे ऐसा कुछ कर सकते हैं क्या?" And you know what is the first thing he says? "अन्ना तू भेजो ना, जो job चाहिए I'll give him." He's like, "मतलब what is his profile? Nothing. You told ना, I'll give a job." I said, "Yeah, don't do all that shit. You call him for the interview. If you think he's eligible, give him a job." So that guy called him on an interview, right? And then he said, "Okay, fine, you can get in, no problem." Right? He said, "Exactly plan kya hai?" So that guy told him, "See, actually मुझे MBA करना है, I want something in management. But no company is ready to give me management का role because I was in civil." This guy said, "ठीक है. So in my company, you work as an assistant manager in so and so place." He worked there for a year. And then this guy wrote a very good review, like he's a very good manager, blah, blah, blah. And he took that and then he applied for IIMs and all. It really helped him when he went to IIM. You tell me, who will help you this much? Your friends will do that. And where do you will get friends like this? If you join your local college as Don Bosco Engineering College, पता है ना, there is a college called Don Bosco Engineering College. All Dons used to study there, I guess. मतलब पता नहीं. It's actually some Christian saint का name. But whenever I hear that name, it gives that feeling, Don Bosco Engineering College. I said, yeah, Don बनोगे यहाँ पे. So there matters. अरे यार, I gave him material. I gave him some 60 GB का material. वो देना ही पड़ेगा ना. He is opening his own institute in Chennai, it seems. He needed help. So your junior, so you help him. तो है. So this is the point. So anytime you feel like, मैं इतना मेहनत क्यों कर रहा हूँ, it is to make good friends. And good friends will matter a lot. So yeah. So but more energy than molecules inside the liquid. Anyways, right? Due to the unbalanced forces. Now, tell me one thing. That means no one wants to be on the outside. So everyone wants to be inside. That means you want to minimize the surface area. So to minimize the surface area, the system will try to have minimum surface area. To minimize the energy, we know, right? Every system will try to achieve a state of least energy. Like I said, if all these penguins are just sitting there and no one wants to die and no one wants to be on the outer surface, we need to make sure the minimum number of penguins are on the outside. That means we need to minimize the surface area. Now in Max, there's a statement like this. I'm not sure whether you know this. For a given volume, the sphere has the least surface area. Do you know the statement? Among all 3D shapes, for a given volume, sphere has the least surface area. That is the reason if you take a liquid and put it in a gravity-free space, it becomes a sphere. So your raindrops is almost spherical. The gravity distorts it a bit, but it actually becomes a spherical. That is the reason any liquid, when you put it in a gravity-free space, immediately it becomes a sphere. Right? And the sphere actually very beautiful properties. For a given system, the sphere has the least potential energy. Ever thought about it? Why planets are round? Why they don't create some other weird shapes? So that is the thing basically. The spheres will have a least potential energy. So how does this look? Let's see how does the spheres look. So we need gravity-free space, so International Space Station. There, can you see that water there? Oscillating a bit because, and there he kept some blue liquid, blue color for us to see. He is keeping an antacid tablet inside. Now, think about this. If you keep an antacid tablet, the carbon dioxide which is produced, normally we burp, right? So it comes opposite to gravity. But here there is no gravity. So there is no concept of up and down. So which way will the gas go? There, can you see how it forms bubbles? You'll get bubbles in all directions. नाइस शेप ना कुछ तो लग रहा है केमिस्ट्री का कंपाउंड जैसा It's like venom itself. I don't know what is venom. The only venom I know is that Spider-Man ka black thing.
Yes, sir, I'm talking about that one.
That only, yeah. So clear with us again. So what is the formula end of the day? Change in surface energy is S into change in surface area. Yeah, straightforward formula. Let's say a question on this. Again, this is another standard model. We got a solid sphere of radius r. It's a liquid dropper. Remember, liquid drop has only one surface. S is the surface tension and R is the radius. So this thing breaks into n identical spheres. Find the change in surface energy. Find the change in surface energy. There, let's get this. Let's see. Again, when you break something into drops, what remains constant? Volume. So volume must remain constant. So this is 4 by 3 pi capital R cube must be equal to n times 4 by 3 pi small r cube. Therefore, small r will be r by n power 1 by 3. This is the radius of small drops. So what is the change in surface area? Change in surface area will be, you can take final area will be n into 4 pi small r square minus the initial surface area 4 pi r square. Remember, total surface area you should take. So the small drop will have 4 pi small r square, but there are n of them. So this would be 4 pi and small r square will be r square by n power 2 by 3 into n minus r square. So therefore, the change in surface energy is S into delta A. This will be 4 pi r square S into n power 1 by 3 minus 1. So if you actually notice here, whenever you break this drop into n drops, the surface energy increases. So where do you get this energy from normally? So when you're spraying the water, you have to give some energy for it to break, and some of the energy comes from atmosphere. Did you ever notice this? When you spray water on yourself, or when you spray water in the surrounding, temperature cools down. कभी try किया? वो होता है ना, when you go to the barber shop, they have that hair का spray, water spray. When you spray that, can you see it feels cooling? Or did you ever use an air cooler? Not AC, not air conditioning. Air cooler कभी use किया? Air cooler looks like this. We have a box kind of thing. We have a big fan here, and on the side there's a grass kind of thing. The water is dripping here, and this fan is blowing air. Ever seen that? Air cooler. Normally, when the temperatures exceed 45-50 degrees, right, ACs don't work that good. We actually use air cooler because this thing will provide humidity also in the surrounding. Nagpur mein people use this when the temperature exceeds 50 degrees. It gets really hot. ACs really don't work. AC ka problem ye hai, it will give you cool air, but it will also remove the humidity from the air. So it becomes very dry. And that's a very dangerous condition. It's so hot and air becomes dry, you will dehydrate without understanding. So air cooler is better. It gives you humidity. It also cools down. So here, when the droplets fall here, they're breaking down into smaller and smaller droplets. They absorb the heat from the surrounding. So temperature inside the air cooler will decrease, and that air you are blowing out. Why all that? Did you ever go under a tree in a shade? It feels more cool. Because in school, you studied this in biology. Under the trees, there are small, small pores where the water is coming out. This is called transpiration. Did you study anything like this? So one of the reasons why you go and stand under a tree, it feels a little cool. Clear with this. We can put ice also. Expensive, but yeah. Let's see one more. We have a soap bubble. Radius R. Now someone, what they did, they kept a small straw inside and you started blowing air inside. The outside pressure is P naught. In this process, what will happen? This soap bubble becomes bigger. Of radius 2R. S is the surface tension. R is the radius. Find the work done by the external force. Find the work done with the person who is making this bubble from R to 2R. So you took a soap bubble, you kept a straw inside and you blowed air. And the bubble ka radius became 2R. Soap is blown from R to 2R. Find the work done by external force. Near area. Let's see how you do that. नहीं यार यार नहीं Srihari, that's not the complete answer. Yeah, that's not the complete answer. Now listen, there are two things you're doing here. Most people don't realize this. Maybe if I had given you options, you would have figured it out. So what you're doing, first of all, you're increasing the surface area. Agreed. That is the change in surface energy. But you're also doing something. When you're blowing that bubble, you're also pushing the atmosphere, isn't it? You're doing work against the atmosphere. This will be S into delta A, the change in surface area, plus this will be pressure into delta V. Did you study this in chemistry? Work done in isobaric pressure, P into delta V. How can you prove that? Force into displacement. Force is pressure into area. Area into displacement is change in volume. Fair enough. So this would be a constant pressure because you're pushing the atmosphere outside. You have to do work on that also. Great. Remember, it's a soap bubble. The 2 into surface tension into change in surface area, 4 pi 2r whole square minus 4 pi r square. This will be P naught into change in volume, which is 4 by 3 pi 2r whole cube minus 4 by 3 pi r cube. And there, most people forget that pressure ka term. So you're doing work in order to increase the surface area, and you're also doing work against the atmosphere because you're pushing the air outside, isn't it? All clear with this? Take a break. Come back by 9:40. We'll continue from here. Any doubts so far? Chalo, come back in 5 minutes. Okay, next thing. So that's a little bit about the surface energy. The next thing, the excess pressure inside a liquid drop. Now remember, just now we made a discussion like everyone wants to go inside. Now in a sphere, if everyone is trying to push inside, doesn't that mean the pressure inside is more than pressure outside? Right? Automatically pressure inside will increase because everyone is trying to rush inside. So consider a liquid. Of radius r and surface tension s. Now, so we took a liquid drop of radius r. Draw FBD of the half drop. Now see, when you draw FBD of the half drop, what are the forces acting on this? One, the atmosphere is pushing you from outside. Now remember, if the pressure is constant, I can use projected area. So atmosphere is pushing with P naught into pi r square. And the liquid is pushing you from inside. So that will be P inside into pi r square. And there is a surface tension. Now where is the surface tension? Remember, it is acting on the circumference. It is acting on the surface. Remember, it's a surface phenomena. Are you able to visualize how is that surface exactly? Did you ever see a coconut? If you see my screen, now look at this thing. If you have a coconut like this, a complete thing, when I open it like this, so the surface tension will be acting on this edge, isn't it? Suppose if you have a coconut or a ball, and if I try to stretch it, how will the force be? Won't the force be on the circumference? Remember, we said it's like a membrane. Getting it? It's like a membrane. So the membrane is on the outer surface, it is trying to pull. And how much is that? Surface tension into 2 pi r. The length. The length is the circumference. And why are you taking only one? Because it's a liquid drop. This pi r square is your projected area. Are those comes on? So now, since the liquid drop is in equilibrium, pressure inside into pi r square will be pressure outside into pi r square into s into 2 pi r. So this gives you pressure inside is equal to P naught plus 2s by r. So delta P is your excess pressure, which is 2s by r. This is for one surface. So inside a liquid drop, because the molecules are trying to push inside, you get an extra pressure 2s by r. Clear with this? So the two main things is a liquid drop and a soap bubble. Let me show you that again. I'll write it down. So if you take a liquid drop, there's only one surface. Now instead of saying inside and outside, you can also say like this. This is P in and this is P out. You can also write this thing as P concave. So if you stand inside, you think the surface is concave. This is your inside. P convex, that is your outside, will be 2s by r. Now for a soap bubble, there are two surfaces. So here, if the pressure outside is P naught, here the pressure will be P naught plus 2s by r because there's only one surface, and the pressure inside will be P naught plus 4s by r. So every surface will increase the pressure by 2s by r. So here pressure in will be P naught plus 4s by r. So each surface will bump up the pressure by 2s by r. So since soap film has two surfaces, you get 4s by r. Clear with this? Now you can have a more general formula for any random surface. Now the proof is not important, but you can remember this. Across excess pressure across a surface. So let's say if you have a surface like this, let's say this radius of curvature is R1, this radius of curvature is R2. So we have two different radius of curvatures. So here, this is your concave, this is your convex. So the general formula will be P concave minus P convex will be S into 1 by R1 plus 1 by R2. This is for one surface. Where R1, R2 are the two radius of curvatures. I'll give you some examples. So, how will the surface kind of looks like? Not exactly this. I'll give you some examples. Have a look at this. So this is our general formula there. Now, if you take a sphere, so you have to take the two radius of curvatures in two perpendicular directions. So for a sphere, this is one radius of curvature. This is another radius of curvature. Can you see there are two radius of curvatures and both are R only. So here R1 is equal to R2 is equal to R. So we get delta P will be S by 1 by R plus 1 by R. 2S by R. For a soap bubble, it will be 4S by R. If you take a cylinder, could be Srihari, could be. I don't know the exact name. If you take a cylinder, how is the radius of curvature? See, basically you have to go in two perpendicular directions. You can go like this. This is radius R. You can go like this. That becomes a flat line. So that radius is infinity. Is that making sense? For a cylinder, the two radius of curvatures, one is a straight line and one is your circle. So you have to take the in two perpendicular directions here. So R2 is infinity and R1 is R. That means the excess pressure in a cylindrical surface will be 1 by R by 1 by infinity, which is S by R. So how can they frame that? Have a look at this thing. So for a surface, right, you have different radius of curvatures. You can even have this weird shape if you remember, which you did in work power energy. So like, something like this. If you see, this is like actually a cylinder. So we are talking about this is one radius of curvature and this is another radius of curvature, which is a straight line. So where do you get these kind of surfaces? If you take two glass plates and put mercury between them, if you put mercury, right, this is how it will look. The mercury will bulge like this. This is mercury between glass plates. If radius is changing at every angle, then every point pressure will keep changing. What is the problem? So here the pressure is P naught. Now see which is concave, inside is convex. So if I take this thing as 2R, then the pressure here will be P naught plus S by R, where this is the formula there. Same thing if you take water between glass plates. We will see later on why this shape forms like this. Use something called contact angle. And the shape becomes like this. So the water becomes like this inside the glass plate. So here, if the pressure is P naught, here remember now this is the concave side. This would be the convex side. The pressure will be less actually, which is P naught minus S by R. Clear with this? So you can get a cylindrical surface when you put liquid between two glass plates. When the liquid gets stuck, you get this cylindrical surfaces. So this is a more general formula for when you know R1 and R2. But anyway, these two are more important, the liquid drop and soap bubble. Clear with this? So let's see a few questions on this. We have a soap bubble and we have a soap bubble. Radius R, radius 2R. I think two drops will do. So we have two concentric soap bubbles. Srihari, ask after the class. Focus on the class right now. So if you take this point as A and if you take this point as B and the outside is P naught, find PA and PB. Easy one, direct formula substitution. Get this. How do we do this thing? Straightforward, right? Again, remember the formula, pressure inside is equal to pressure outside plus 2S by R. So PA will be P naught plus it's a soap bubble 4S by radius, which is 2R. What is pressure at B? Pressure outside, which is PA plus 4S by radius. Easy? Got this. You just have to add them and you're done. So every soap bubble will just keep bumping up the pressure. Yeah, that's an easy one. Next one is another theoretical question. if you have two soap bubbles, a big one and a small one, so this is R1 and this is R2. R2 greater than R1. Now, if you connect them with a pipe, in which direction does the air flow? Small to big or big to small? Again, straightforward. Air always flows from high pressure to low pressure. This is P1, this is P2. So P1 is P naught plus 4s by R1, and your radius is smaller. P2 is P naught plus 4s by R2. Since R2 is greater than R1, P2 is less than P1. So most people think, the big one the air will flow from big to small and they become equal. It's not like that. Air actually flows from high pressure to low pressure. So air flows from R1 to R2. The smaller becomes smaller, bigger becomes bigger. And eventually the smaller bubble will just become like a drop. Clear with this. So if you take a small one and a big one, air flows from smaller to bigger. So be careful with that. Let's see something little better. So we have a soap bubble. Radius R, filled with air. Coefficient of viscosity is eta. S is your surface tension. Outside pressure is P naught. Now what you did, you took a small pipe. L is the length of the pipe. Small a is the radius of the pipe. Now because the pressure inside is more than outside, the air will start rushing out through the pipe. Now if the air starts going out, the radius will start decreasing. So the air will start going inside and the air starts leaking out. Find the radius of the bubble as function of time t. They're a combined viscosity with surface tension.
Sir, can
And
you
radius
please
of
show the Poiseuille's equation?
why? Don't remember.
Yes.
Bubble at a time. Poiseuille's equation क्या था? Volume per second is pi delta p r power 4 by 8 eta L. There, in case you forgot, we have to use that Poiseuille's equation to solve. And remember that smaller is the radius of the pipe, not the radius of the bubble. There, get it. Now, because the soap bubble will have more pressure than outside, the air will start going out. If the air goes out, the radius will change. So find the radius of the bubble as function of time. Right. Get the equations. Let's see. R power 4 T. R power 4, you got it like that, क्या? Numerator में आया. Hmm. Okay, looks right. But minus sign आएगा ना, सम्यक. Look at ना, in this case your bubble का radius is increasing. When you wrote that volume, na, volume is decreasing, na, should put a minus sign. So look at the equation here.
Like I'm getting it, but it's in form of a equation which we'll have to solve for R.
नहीं इतना कुछ नहीं है. You'll get decent only. There. So let the radius become x. So what is the volume? The volume is 4 by 3 pi x cube. So the change in volume dV will be 4 pi x square dx with a minus sign. Negative because the volume is decreasing. And what is the pressure inside? Pressure inside at any instant will be P naught plus 4s by x. So if you actually observe, as the bubble becomes smaller and smaller, the pressure is actually becoming more and more. That means it will actually start leaking out faster. And outside the pressure is P naught. So the pressure difference delta P will be 4s by x. Now using the Poiseuille's equation, that is d volume by dt, that is your volume flow per second, is pi delta P a power 4 by 8 eta L. So this would be 4 pi x square by dx by dt. Pi, pressure difference is 4s by x. This is a power 4, constant, 8 is constant, eta is constant, L is constant. So bring all x to one side. This guy will be minus x cube dx. Pi and 4 will go off. You end up with s a power 4 by 8 eta L dt. Integrate, this will go from r to x and this will go from 0 to t. That would be x power 4 minus r power 4 by 4. Let's say power 4 by 8 eta lt. Send that 4, that side 2 will cancel. Send minus also, we'll get x power 4 is equal to r power 4 minus s a power 4 time by 2 eta l. Check. So you can put the power fourth power and you'll get the answer there.
So we can use binomial approximation.
कहाँ पे?
Sir, to find value of x.
Why? इतना काम क्यों करने? Whole power 1/4. You're done.
I mean, just to simplify it.
अरे, you can use binomial only when it is very, very small, right? You can't use binomial wherever you want. If is 1 plus x whole power n is approximately 1 plus nx, if x is much, much lesser than 1, for example, if someone gives you 1.001 ka whole power 1 by 3, then you can write this thing as 1.001 power 1 by 3. इसका approximation होता है. What you're doing, God, 3 power 1 by 3. तो तेरा approximation 1 plus 2 into whole power 1 by 3. तो 1 plus 1 by 3 into 2 डाल दे. You can't do that. Binomial, it has to be very, very small to approximate. Don't use it randomly anywhere. Are you clear with this? All got this? There, Poiseuille's equation, soap bubble का excess pressure. Next one. Let's say we have two soap bubbles, S, another soap bubble, surface tension S. These two soap bubbles got combined into one big bubble in surface tension S. Now, we don't know the radius, we don't know anything. Two soap bubbles, outside pressure is P naught, that is there. Combined to form one big bubble. And it is given delta A is the total change in surface area. Delta V is the change in volume. Find relation between delta A and delta V, assuming isothermal conditions. Meaning, assume temperature remains constant in this process. And the gas is ideal gas. Assume isothermal conditions and ideal gas. So we have to use PV is equal to nRT. Let's see how we do this. So you have taken two soap bubbles. You can start like this. Let the radius be R1, let the radius be R2, and let the final radius be R. End में you have to eliminate R1, R2, and R. Let's get this. This is more of a ideal gas equation kind of question. Two soap bubbles of some unknown radius, when they combine, they get one bubble. The change in area is delta A, and the change in volume is delta V. Find the relation of delta A and delta V. So they can simply ask like delta A by delta V is how much. Let's see. How do we do this? So we have two soap bubbles. They became one big one. So let the radius be R1, let the radius be R2, and let the radius be R. So what is the pressure inside? So P1 will be P naught plus 4S by R1. What is the pressure here inside P2? P naught plus 4S by R2. And what is the pressure here? P naught plus 4S by R. Now tell me one thing. When you combine both the bubbles, what remains constant? What remains constant? The pressure. Temperature is given constant. Will the volume remain constant? Will the pressure remain constant? So P1 V1 is equal to N1 RT. P2 V2 is equal to N2 RT. Number of moles will remain constant, isn't it? So the final P final V final must be equal to N1 plus N2 RT. So number of moles will remain constant when you combine two gases. This would be P1 V1 plus P2 V2. Yeah, you're done. So what is P final? There. Now, if you take this equation here and if you try to simplify, you'll actually get what you want. So bring all P naughts to one side. That will become P naught 4 by 3 pi r cube. 4 by 3 pi r1 cube r2 cube. Bring it this side. This guy will become 4s by 3 4 pi r square minus 4 pi r1 square plus r2 square. There, you're done, right? So this whole term inside is change in volume. This whole term inside is change in area. So P naught delta V plus 4s by 3 delta A is 0. 3P naught delta V plus 4s delta A is equal to 0. That's the relation between them. Is that clear, everyone? Got this? So then basically I found the pressure inside, then I know the volumes. I used PV is equal to nRT, and when you combine them, the number of moles will remain constant. So the P final, V final must be equal to the total number of moles into RT. Total number of moles are N1 plus N2, but N1 RT and N2 RT are P1 V1, P2 V2. Then it is just a matter of solving there. Check. All clear with this? Any doubts on this? Let's see one more. This is another standard means level question. You should definitely know this. Comes a lot. Two soap bubbles coalesce. So it's a fancy way of saying, the soap bubbles stick to each other of radius R1 and R2 coalesce. Meaning the picture will look like this. This is one bubble, this is one bubble, and this is your interface. This is R2. This is R1. This here is your interface. And if you extend this, that would have been a full bubble, but yeah, part of it. Find the radius of the interface. And find, now when you look at this, here, at this point, you actually get angles. This angle is alpha, this angle is beta, and this angle is gamma. So alpha, beta, or the gamma are the angles at the point where the three surfaces meet. This is the point where R1, R2, and R meet. Meaning the picture, right, will look like this. If you ever seen a soap bubbles, right? There. I know here there are three soap bubbles are stuck, but I hope you can see the picture there how it is. So this is what I'm asking in the inside one. Can you see this is the interface? How do you find R1 R2? Let's get this thing. You should definitely mug up the result, both of them. नहीं आ रहा नहीं right here. Right, Trishi. Get me the angles also. Let's see. Again, we just have to use the pressure ka thing. So we have one interface here, and we have one interface here, and this is there. Now, if you just go and stand here, now ask yourself, okay, this is P naught. This is your R2. So the pressure will be P2. So P2 will be P naught plus 4S by R2. This is your R1 here, and this is P1. So P1 will be P naught plus 4S by R1. So now if you look at the interface, what will the interface think? Interface will think, okay, I'm a new bubble. Now, it's not a complete one, right? And this side is your concave, and that side is your convex for the interface. That's what I said. Instead of thinking inside and outside, it will get confusing. It is better you use concave and convex. Wherever the pressure is more, the surface will become concave. It will push. Wherever the surface is less, become convex. That would be 4S by R. So basically, P1 is your concave thing. So this is P1 minus P2 is 4S by R. So that would become 1 by R is equal to 1 by R1 by 1 by R2. The radius of curvature will be R2 minus R1 by R1 R2. I reverse R1 R2 by R2 minus R1. So what do you mean by is, let's say if R2 is less than R1, you'll get R negative. Means what? The surface is not like this, surface is like this, isn't it? The curvature becomes concave to convex. So the sign will take care whether if you're taking it wrong, the sign will take care of it. If you got negative, it is not like this, it is like this. the other way. Is that clear, everyone? And if you take R1 is equal to R2, we get the radius of interface is infinity. What is infinity? A straight line. Meaning the bubbles will look like this. So the interface will be perfectly a straight line. Yeah. Now, what about the angles here? Now, listen to the angles part here. So if you draw the FBD of this part, this is how it will look. Now look at the argument here. Just before this interface at these 3 points, the pressure must be equal. Why? If the pressure is not equal, then the soap solution will keep moving until the pressures become equal. Do you agree with that statement? At this point, the pressure, whatever force it is acting on that small area, if you take a small area dA in this center, the liquid is pushing from all three directions. So basically, this is your soap solution. The pressure at that point, or the force due to the pressure from that point, should be same in all directions. Pressure is same on all three sides. Because if they're not equal, the soap solution will keep moving. And it will keep moving till the pressures balance out. Now you tell me, from vectors, if you have three equal forces and the point is in equilibrium, what is the angle between them? 120 degrees, isn't it? So if you have three equal forces and if they're in equilibrium, they'll form the sides of a triangle. So it'll form 120 degrees. Therefore, alpha is equal to beta is equal to gamma is 120 degrees, independent of R1, R2. That's the best thing about that result. It doesn't matter what kind of radius you will take, the angles will be always 120. That's why I said the result is important, because examiner they'll say R into R and you'll get confused like, oh, how to calculate that? Is this clear, everyone? They'll always make 120 degrees independent of the radiuses that you take. All clear with this? Now, let me show you something. So how to make a soap bubble? You take dishwashing water. So normally when you try with surf, right, you really don't get good bubbles actually because they're little thin. So you have to add some glycerin. If you add glycerin, you get very thick bubbles. So this is what actually they sell near the beaches and all. So he took a pipe, a washing machine ka pipe hota hai na, that one. He cut it. He made a circle. He stick this. He made a round frame there. So basically, you can make that thing to make a soap bubble like that. There he made a handle. There he added soap solution. दिख रहे soap bubble? Look at this thing. This we will see in electrostatics. You must have learned this in school. When you take a piece of paper and rub, it attracts things. So bubble gets attracted. Electrostatics. There you can put a soap bubble inside. Inside. So every time it put a soap bubble, pressure keeps on increasing. It goes off. So there, it is the thing. Now, one important thing, if you observe when he's touching, right, nothing is happening. So the thing is, when you touch something, if you put your hand in a soap solution and if you touch the bubble, nothing happens. But if you touch with your dry hand, soap bubble pops. So he's touching with a dry hand. Now this is important. I wanted to listen to this thing. See what he's doing. He took two rings there, and when he's blowing a bubble, you actually get two bubbles. You get one bubble because of the small ring, and you get one bubble because of that big ring. There you got a soap bubble. So there are actually two bubbles inside. If you can see, there's a shade. Now he's filling inside with some hydrogen gas. And we can't see the gas, right? So he'll put some smoke. Then now you can see the gas. There. Now we got a bubble filled with smoke, and at the top, remember, there's a small hole. So he's popping that bubble on that thing. Now remember the formula, inside is P naught plus 4s by R. So pressure is more than outside, so the gas will start leaking out of the hole. Now if the gas starts leaking, radius becomes smaller. If the radius becomes smaller, then the pressure is more, so gas will come out even faster. Now if the gas comes out faster, and if you put a fire, what should happen? The fire should become bigger and bigger. There he puts a fire. Can you see the flame? Look at the size of the fire, flame. It is becoming bigger and bigger. So that is how you know, like, the pressure is increasing more inside. Smaller bubbles have more pressure. And you can see that in the slow motion. You can see how that you get a whirlpool kind of thing inside. It's just pulling the air out. And you can see the size of the flame becomes bigger. You can even make, this is the circle thing. This is the drinker thing. I'll send this. You can have a look at. This is also fun, actually. See, you put dry ice, and then you put soap solution on top of it. It's literally floating by and force. Carbon dioxide is heavier. He's putting liquid soap. There you get a big soap bubble. वो होता है ना दिवाली में वो snake, the black thing, when you burn that comes. This is a white snake. Surface tension. Can you see clearly? It's acting like a membrane. It is not letting the air go out. And there it goes on and on and on. So that's how the soap bubble looks. Do I have one more? Yep, that is the thing. Clear with this? So there you can see the soap bubbles, right? The pressure and all that stuff. Okay, with that we'll wrap up for the day. Next class when we catch up, we'll continue from here. We are going to see something called capillary action. Mostly I think next class we will wrap up the chapter. maybe a little might be left over. Like I said, it's a small one. After that, we'll start off with elasticity, and then we'll go with thermodynamics. Okay, that will wrap up for the day. I'll see you guys again on Thursday, same time. So, any doubts, anything else, please stay back and ask. I'll be free to leave. So, take care.